Today, I'm going to be teaching you about the Intermediate Value Theorem, or IVT. Whenever you want to use the IVT as reasoning for your solution in a problem, you always need to state its conditions and then what it actually proves. So first, we have its conditions specified by an if statement. So in order to say the IVT applies, you first have to prove that f of x is continuous on the closed interval a to b. Then, once you do that, you can actually apply the intermediate value theorem in its whole. So the IVT states that given f of a is less than some constant a is less than f of b, there must be some value c for which f of c equals a. So to break this down, this is saying that whatever the y values of these two boundaries a and b, there must be some y value between them as long as the function is continuous. So once again, it's really useful to look at a graph to explain this theorem. And so let's say our interval is from x equals 1 to x equals 3. So that's going to be our a and b in this situation. Now, given that the y value at x equals 1, it's approximately 1/2. So we're going to write 1, 1/2. And given that the y value at x equals 3 is approximately 4, so we can write 3, 4. We know that in this interval, in the middle of those 2 points, there has to be some y value which is greater than 1/2 and less than 4, which is where we get this inequality here. However, we only can say that this is true if the conditions of the IVT are met, which is that this interval is continuous. So in short, what this theorem is stating that if you have a point A and you have a point B and you have a line connecting these 2 points, there is also a value for everything between A and B. And this is going to crop up a lot in AP Calculus AB FRQs, so we're going to go ahead and actually practice one of those FRQs from a past exam. So we're going to be practicing the 2007 AP Calculus AB FRQ, specifically question 3. And you always want to start off an FRQ by reading the information that it gives you at the beginning. So here we have that the functions f and g are differentiable for all real numbers. And if you haven't learned about differentiation yet, you can basically know that if a function is differentiable, that it's also continuous. So f and g are continuous for all real numbers, and g is strictly increasing. The table above gives values of the functions and their first derivatives at selected values of x. The function h is given by h of x equals f of g of x minus 6. So when the question gives me a new function, like h of x, I always like to rewrite it up here. This is just preference, but it just becomes a little easier for me to work with it from there. Now the actual question is asking us to explain why there must be a value r for 1 is less than r is less than 3, such that h of r equals -5. And this inequality here is going to clue you into the fact that you have to use the intermediate value theorem, specifically to prove that there is some y value between 1 and 3, which equals -5. So the first thing we want to do is find the y values that correspond to x equals 1 and x equals 3. So first of all, we're going to find h of 1 because 1 is the lower boundary. So if we plug in 1 directly, we get f of g of 1 minus 6. And for this problem, we're going to have to refer to the table to figure out what g of 1 is. So we can see with the table that at x equals 1, g of x equals 2. So we're going to get f of 2 minus 6. Once again, using the table, we see that at x equals 2, f of x equals 9, leaving us with 9 minus 6, which equals 3. Next, we need to find the upper boundary of this inequality, which is h of 3. Once again, we're just going to directly plug this into the equation, get f of g of 3 minus 6. Now we're going to ignore this f for now and just figure out what g of 3 equals. And using the table, we see that at x equals 3, g of x equals 4, so we get f of 4 minus 6. Using the table, f of 4 equals -1, leaving us with -1 minus 6, or -7. So we now know the boundaries of this inequality, and so we can kind of set up an inequality over here, like so, which we're now going to use to see if -5 is within that boundary. So writing in -5, because that's the y value we're trying to discover here, we can see that -5 is greater than -7, as well as less than 3. So we can now state the conditions of the IVT and its conclusion to answer this question. So we're going to start off by saying because h of x is continuous for all real numbers, which was provided to us in the problem, and because we need to state the inequality now, which is that h of 3 is less than -5 is less than h of 1. By the intermediate value theorem, which I'm going to abbreviate to IVT, there must be a value r such that h of r equals -5. And so the two biggest takeaways from this is that you need to state that the function is continuous and you need to provide an inequality. And I've pulled up the scoring guidelines for this FRQ on screen, and we're going to use this to grade ourselves and see how we did. So there's going to be 2 points for this FRQ specifically, and we can see that the first point is acquired from finding h of 1 and h of 3. Specifically finding that h of 1 equals 3 and that h of 3 equals -7. So we get the first point for this. Next, we get a point for stating our conclusion using the IVT. You can see here that they have an inequality, and they also state that h is continuous. So our conclusion also gets a point, meaning we get full points for this FRQ. And again, all we're really proving with this intermediate value theorem is that we have some point down here, -7. We have another point over here, 3. So there has to be a value in between this line, no matter what trajectory it takes, for which y also equals -5. And we only know this because, again, the function is continuous. Another way you could use the IVT is to show whether a function has a 0 or x-intercept within an interval. So let's say we want to find out whether there's an x-intercept on the interval 1 to 3. Now, if we just think about this logically, we can see that at x equals 1, we have some negative value, and at x equals 3, we have some positive value. And so given that this curve is continuous on the interval 1, 3, there must be some value between 1 and 3 that y equals 0. Because in order to go from negative to positive, the function has to cross the x-axis. So we're going to apply this to a problem which asks us to use the IVT to verify that x cubed minus 2x squared plus x minus 1 has a 0 between 1, 2. So first of all, we want to check that this function is continuous on the interval 1, 2. Because if it's not, then we can't even use the IVT in the first place. Now we know that the graph of a cubic function with x cubed in it is going to follow some kind of curve that looks like this. And in my introduction to calculus video, we actually learned that cubic functions are one of the functions which are continuous for all points. So therefore, we can establish that this function is continuous on the interval 1, 2 because it's actually continuous for every point that exists. So now that we've established continuity, we can move on to step 2, which is finding our inequality. So we're going to put 0 in the middle here because we're trying to find whether or not there is a 0 which exists. And hopefully these two numbers we get on either side do satisfy the inequality. So we're going to start off by plugging in 1 to this function, which would give us 1 cubed minus 2 times 1 squared plus 1 minus 1. Simplifying this, 1 cubed equals 1, 2 times 1 squared equals 2, and then 1 minus 1 is 0. So we're left with 1 minus 2, or -1. So starting off strong, we have -1 is less than 0, which is a true statement. But we're going to see if this still holds up when we plug in 2, which will give us 2 cubed minus 2 times 2 squared plus 2 minus 1. Now, 2 cubed is 8, 2 times 2 squared is also 8, and then 2 minus 1 is 1. So, 8 minus 8 cancels out to 0, and we're left with simply 1. And then plugging this into our inequality, we see that we still have a true statement. -1 is less than 0 is less than 1 is a logical inequality. So the IVT holds up. Again, we're going to write our conclusion. First of all, saying that because x cubed minus 2x squared plus x minus 1 is continuous on the closed interval 1, 2, and because -1, we're going to plug in the inequality here, -1 is less than 0 is less than 1, there must be a 0 between the interval 1, 2. So now that we've done a couple examples, hopefully you have a little bit more of a firm grasp on the IVT. Again, this is a really good tool to have for FRQs, but other than that, I hope you guys learned something. Comment down below anything you would like me to make a video on in the future, and thank you.